Today we have Keeper 4.3, particle motion. All right, so let's just start off with a basic start or a basic example for particle motion. We'll get a little bit harder as the questions progress. So it says answer the following questions for each position function or for this position function S of t in meters where t is in seconds if a particle is moving along the x-axis. So I'm giving you a function S of t equals t cubed minus 6t squared plus 9t. The very first question says find the velocity. What we need to understand is that velocity is the derivative of the position function. So whatever the position function is, in this case S of t, we simply need to take the derivative to find the velocity. So I'm using power rule, I'm going to get that v of t is equal to s prime of t, or v of t is 3t squared minus 12t plus 9. Part B says, well, what is that velocity after 2 seconds? Well, in other words, they're telling you that t equals 2. So everywhere I see a t in my velocity equation, I'm going to replace it with 2. So v of 2 equals 3 times 2 squared minus 12 times 2 plus 9. When I simplify that, I get 12 minus 24 plus 9, which equals negative 3 meters per second. Make sure that you guys put units on your measurement. So don't just say negative 3. You must give me some units. In this case, is meters per second. All right, next it says find the acceleration. So for us, our formula for acceleration is the derivative of your velocity, or you can look at it as the second derivative of your position. So again, in order to find acceleration, I can either take the derivative of the velocity or the second derivative of position. So if I start with my velocity equation and take the derivative of that, I'd be left with 6t minus 12. Now, if I need to find the acceleration at t equals 3 seconds, everywhere I see a t in my acceleration problem or my acceleration formula, I'm putting in 3. So I get 6 times 3 minus 12, which is 18 minus 12, which is 6. And our units for that, again, is meters per second squared. All right, so again, anytime I'm working with velocity, is meters per second, versus when I'm doing acceleration, is meters per second squared. All right, moving to some intermediate level problems. This question asks, when is the particle at rest? Well, in order to determine when the particle is at rest, we need to take our velocity and set it equal to 0. So our velocity formula was 3t squared minus 12t plus 9. I'm going to set that equal to 0. Using basic algebra, I'm going to divide everything out by 3 to get t squared minus 4t plus 3. And then I'm going to factor that to t minus 3, t minus 1, and set that equal to 0. From there, I could take each factor, set them equal to 0 individually, and I get t equals 3 seconds, t equals 1 second. Again, please note that I am putting units. All right, I'm not just saying t equals 1 and t equals 3. I made sure that I said second after each one. All right, part F says, when is the particle moving forward or when is it moving right? They could have asked also, when is it moving backwards or when is it moving left? To determine that, you're going to take the values that you got from when your particle is at rest, and you want to figure out where is it greater than 0 to figure out where it's moving forward. So again, I'm going to take that 1 and that 3 that I got from part E, and then I'm going to put them on the number line, and I'm going to plug numbers into my velocity formula to see when is it moving plus or when is it moving minus. Now, if you remember, our velocity formula was 3t squared minus 12t plus 9. That is a quadratic equation and it's pointing upwards because it's positive. So I know by default, without even having to plug in numbers, I know that the outsides are going to be plus and the insides are going to be minus because, again, it had to be a quadratic equation pointing upwards. So when is it moving right? Well, it's moving right wherever I have positives on my number line, and that would be from 0 to 1. Notice I'm starting at 0 because my time can't be negative. And it's also moving right from 3 off to infinity seconds. All right, so here we get into like the top level type problems. The question asks, what is the displacement on 0 to 5 seconds? So now I'm giving you a bound. I'm saying only go from 0 to 5 seconds, not off to infinity. The way that we find displacement is we take the position function at the largest time, and we subtract it from the position function at the smallest time. So s of 5 minus s of 0. All right, so to find this out, I'm just going to plug in 5 into the equation. So I get 5 cubed minus 6 times 5 squared plus 9 times 5. Notice I'm plugging it into position, not velocity, not acceleration. And then I'm going to subtract that by plugging in 0, or s of 0, and I get minus 0 cubed plus 6 times 0 squared minus 9 times 0. Simplifying that, I get 125 minus 150 plus 45, which is 20 meters, again using units. Our displacement is in meters because that's how our particle is moving. It's moving in meters. All right, the next question says find the total distance traveled on 0 to 5. So again, the difference between displacement and total distance is that displacement is telling you how far you are when you finish from where you started. So you could have like walked forward and then came back a little bit. You might not be that far from where you actually started. Versus distance traveled takes all your distances, whether it's going positive forward or negative backwards, and it adds them all up. So even though I walked forward and possibly came back some, I'm getting the total amount that I actually walked, not the distance from start to finish. So total distance traveled, basically I want to take my numbers from my velocity for when it was at rest. I want to use that as like stopping points because that's where it was at rest. So I'm going to go from 0 to 3, and then from like 3 to 5, that type of situation, so I know where I am at rest. All right, so again, total distance is the distance forward plus the distance backwards, making sure that the distance backwards is actually absolute value because I don't want to compute it as a negative. I want to compute it as a positive value. All right, so the distance forward would be from s of 1 minus s of 0, which is 1 cubed plus 6 times 1 squared plus 9 times 1 minus 0, which is 4. And then I walk backwards from 3 to 1, or from 1 to 3. So then I calculate that out, plugging in 3 and plugging in 1. And I get the absolute value of negative 4, which is 4. Now, again, I don't want to use negative 4 because that's going to negate the problem, or it's going to take away from where I walked. I want to still contribute that as me walking. I don't want to look at it as me walking backwards. And then finally, I need to go forward one more time, where I went positive one more time from 3 to 5. So I'm going to do s of 5 minus s of 3, and I get 140. All right, so to get my total distance traveled, I'm going to add up all those values, 4 plus 4 plus 140, and I get 148 meters. All right, next question says, find the velocity when the acceleration is 24 meters per second. Well, I'm simply going to take my acceleration formula and set it equal to 24 to figure out what time I was at when the acceleration was 24 meters per second. So if I add 12 and divide by 6, I get that at t equals 6 seconds, my acceleration was 24 meters per second. So now if I want to find the velocity, I would just simply take that 6, plug it into my velocity formula. So I'd get 3 times 6 squared minus 12 times 6 plus 9, which simplifies out to 108 minus 72 plus 9, which is 45 meters per second. All right, very last question. It says, when is the particle speeding up or slowing down? To determine when the particle is speeding up or slowing down, we have to compare the velocity and the acceleration. All right, so first thing I want to do, like off to the side, is I want to figure out what the acceleration is, or what the t value is when the acceleration equals 0. So I take my acceleration function, 16 minus 12, set it equal to 0, and I find that my time is 2. So now I'm going to take my velocity line that I found way back whenever, and I'm going to compare that to an acceleration line using 2 as my breaking point. And again, because this was a linear function, my acceleration was a linear function, and it was positive, I knew it was going up to the right and down to the left, so I could simply put negatives and positives on my number line. Now, in comparing this, I want to kind of break up my line for every place, every like stopping point. So at 1 and at 3, that's the stopping point for velocity, and at 2 was like a breaking point for my acceleration. Now, wherever your signs for velocity and acceleration are the same, we know that the particle is speeding up. Now, wherever your signs for velocity and acceleration are different, your particle is slowing down. All right, so I have speeding up from 1 to 2 because both of these are negative. So from 1 to 2, I'm speeding up. And also from 3 to 5 because all of this is positive and all of this is positive. So our signs are the same in those two areas. That means I'm speeding up. I'm slowing down where the signs are different. So I'm slowing down for 0 to 1 because I have positive velocity with a negative acceleration. And then I'm also slowing down from 2 to 3 because I have a negative velocity and a positive acceleration.